Hello everyone, this is Cody Jackson for Codamom. Apologize for the lack of videos recently. I have been promoted to senior team lead for the software team, and half of the team has been moved over to other projects, so I have a lot more to do. Karina and Taryn have started new jobs, and so they are heavily invested in learning new skills necessary for those jobs, as well as just personal development. So between the three of us, there's just not going to be a lot of content on here. I can't even guarantee a weekly basis, although we will do our best. That out of the way, this video is part of the IT learning series that we're doing. This time we are talking about CPU operation, specifically how CPUs process commands and make the computer do something. So before we really get into it, I just kind of want to show a diagram of what all of the parts are within a CPU. So when you see a picture of a CPU die, say from Intel, and it has a holographic kind of sheen to it, and you can see that there's different areas on there, but you don't know what they do. Hopefully this will kind of give you an idea. So recognize that for this particular picture, this is an Intel Pentium 5, so this is very old. The current ones are the Cores and the Xeons. So the Pentium 5 was just a single discrete CPU on its own, on a die, on a chip that was in a computer. So I apologize if you hear a lot of cars and motorcycle noises. It's Sunday, and apparently this is the day that everybody decides to go out and make a lot of noise. Anyways, what I was saying is, for the Intel Pentium 5, you can see that the date listed on the graphic is 2003. So this is a very old diagram, but it works for our current purposes. And those current purposes are to show all of the different sections that you can see on a CPU. Now, granted, if you're looking at an actual die of a CPU, about the only thing you're really going to be able to see is where these cache portions are, and then basically just everything else is just, it doesn't look terribly different. So these are kind of singled out because you have a bunch of rectangular blocks where the cache chips are located, and then everything else just looks shiny in the pictures. But you can go to this website, chiparchitect.org, and you can take a closer look at what this particular Pentium 5 chip looks like, or you can pause the video and read all of the text that is here. But you'll see that we have various caches, instruction decoders, predictors, multiple pipelines, front side bus interface, the integer execution area, multimedia capabilities, floating point registers, blah, blah, blah. There's a lot going on here. Now, the catch is, this is a single chip, which would be a single core. Nowadays, we have multi-core chips, so everything you saw on that previous slide is actually contained within one of these CPU cores. So this has been duplicated 8 times for this particular chip, which is a Sandy Bridge layout. In this case, the caches are set up so each CPU core has its own cache, but they can share data between each of those cores by accessing the this ring bus here. By accessing this ring bus that basically allows the cache to access the memory agent, which is then processed into your I/O, or the input-output connections that goes to RAM. So these portions here, physical 1, physical 2, actually connect to the RAM on the motherboard, takes data from that passes it into the memory agent, and then passes it onto the appropriate cache for that specific CPU. But data can be shared as necessary. There's also our physical connections to the South Bridge. So if you remember on a previous video, we talked about North Bridge handling memory, the South Bridge handling the physical connections on the motherboard, and how a lot of those physical connections have now been moved to the CPU. So instead of having a PCI card separately or a physical chip on the motherboard, that PCI connection has been moved to the CPU right here. So now we have the PCI controller, and then we have the physical connections that go out to the motherboard from here. The QPI connections up here is Intel's proprietary Quick Path Interconnect or interface. Regardless, it has replaced the front side bus and is a point-to-point protocol. So basically, rather than having a single bus, so think of a connection on the motherboard where all of the devices connect to, and you have to know the interrupts and the physical addresses of those locations. This is a point-to-point connection, so every device has a dedicated line to it. And this allows the system to work much faster because you don't have to worry about data getting to the right connection on a bus and waiting for the other connections to communicate. Every device has its own dedicated connection, and so the CPU can talk to all of those devices simultaneously if it needs to. There's also the power control unit. That is for the CPU, handles the power for the CPU, and that's primarily for the dynamic changes to the not only power allocation, but it also integrates with how the CPU handles the processor speeds. So because you have multiple cores on here, not every core is going to be working at the same speed depending on what's going on. So you may have some cores running at, maybe 30 megahertz less than optimal performance, or I should say maximum performance, because it doesn't need to. The power control unit can, depending on how the software is designed and the operating system and a lot of other factors, the power control unit can actually shut down portions of the chip that are not being utilized. And in a desktop computer, this will help alleviate some of the power usage that's being used for the computer if it doesn't need everything. For example, if you're just doing basic word processing, you don't need to have everything running at top speed like you would if you were running a AAA video game. So it will power down either the voltages or completely power down different parts of the CPU block. So that could be individual cores, it could be parts of those cores, it could be parts of the CPU itself. Whatever the case may be, the power control unit will handle that to reduce the power usage. Obviously, in laptops, this is very beneficial because the more power that's being used, the more energy is being taken out of the battery. So if you can minimize the power usage by throttling the frequencies of the cores or turning off certain portions that don't need to be used, then you increase your battery life. So I hope that made a little bit of sense. These pictures were just a brief overview of how big scale a CPU looks. And now we are going to go over and actually look at how operations are handled by a CPU based off of the instructions that are coming in. So the following slides actually come from Dr. Chung, hope I pronounced that correctly, from Emory University, and this is part of the CS170 course that he teaches. You can find more information at the URL that I provided on the screen. I reached out to Dr. Chung and got permission to use these slides in this video, And if you have any questions or you want more information, please reach out to him. And he was more than willing to allow me to use this, and so I greatly appreciate Dr. Chung allowing me to use these slides to teach this video. So like I said, these slides are provided by Dr. Chung, and so we are going to talk about the structure and operation of the CPU. It's not going to be as detailed as the pictures that we saw of the actual die, but basic block diagram so you understand what's going on. The program flow and the types of instructions that a computer can actually execute within the CPU. So first we're going to talk about the structure and operation of the actual central processing unit itself. Within the computer, you have a lot of registers, and registers are actually just memory locations. You have general purpose registers, which are used for the vast majority of the calculations that are going to be done. They're general purpose. They can be for anything. There's an ALU, which is the arithmetic logic unit. Its purpose is strictly for arithmetic and logic calculations, and then it passes that data over to a register as needed. You have some other registers that do different things, but these are primarily designed for handling the commands that this CPU is going to be getting. So you have the instruction register, the program counter, the processor status register. Those are more or less incremented, and the data that they capture is provided over into a general purpose register for some sort of calculation or execution. And then there's also the connection to your memory, which handles the addresses for the data that you want to work with. This description right here is one memory cell within RAM. This could also be cache, if you wanted to think of it that way, because realistically cache is just a collection of the most commonly used data and operations from RAM. So within the CPU, the general purpose registers, as I said, a register is basically memory. A general purpose register is just a memory cell. And so it's just a location of where data can be placed. Each general purpose register has a unique name. There's multiple general purpose registers within a CPU. And so the CPU has to be able to tell where the data that it wants is located. Hence, each register has a unique name. It is used to store and recall the intermediate result of complex computations. So basically what that means is, as the computer is making its calculations and doing its command operations, the general purpose register is where each of those intermediate steps before the final command is processed, that intermediate result is stored within that register. The ALU, as I said, is only for your mathematics and logic operations. It's specifically designed to handle those very quickly, so you don't have to deal with the slower general purpose registers to handle those types of operations. The output of the ALU is basically stored within the general purpose register. So while you may have two general purpose registers that have integer values and pass those to the ALU to calculate, say, an addition, and that's put into the result of that, the sum is passed into a third general purpose register to store it. Your instruction register contains the current instruction that is being used by the CPU. It performs the operation indicated by the instruction code that is contained in the instruction register. Basically what that means is the instruction register is the data, the command, whatever the CPU needs. The instruction register holds that particular information within the instruction register, and the CPU uses that for the next process. The program counter holds the address location for the next instruction. So the instruction register is the current instruction. The program counter has the location of the next instruction. And that is incremented sequentially after the instruction is processed. We'll go through this step by step so you get a better understanding of what I'm talking about, but hopefully you see what's going on. The instruction register is your current, your program counter is your next. Process status register is has general information about the CPU as needed for processing, but its most important use for our purposes is the result of a comparison. So when the CPU compares two numbers, the outcome of that is stored into the processor status register. And the outcome can be equal, not equal, less than, greater than, less than or equal to, greater than or equal to. So it's basically where your logic comparisons come from. If you think about programming, then that would be like an if item is equal to another item, do this, so on and so forth. This is basically a physical representation of that. The CPU works automatically, sequentially, generally speaking, and repeatedly. So, assuming you're just running a general command or a general program, and we're right in the middle of it. So, we've just executed an instruction. The CPU knows where the next location is. That's the address location, because that is stored in the program counter. That instruction from memory, from that memory location, the address is pulled and stored into the instruction register. So that's the actual instruction, not the address. The program counter is increased to the next instruction location. So generally speaking, all of your necessary commands are stored sequentially. So once the first instruction is pulled into the instruction register, the program counter is increased to the next location because it's sequentially right next to it. The instruction that was pulled from memory into the CPU, the instruction register, is then processed by the CPU based off of whatever that instruction tells the CPU to do. Once that instruction is processed, then the next instruction from memory is pulled into the instruction register for use. So, we've just finished executing an instruction, and so the instruction register holds the value 0 because that was the code that was put into it. The counter has the location of the next instruction, which happens to be location address 1, and then the PSR has the outcome of the last compare operation, but that's irrelevant to this point. Instruction code 0 in the instruction register means add and has just been executed. So we know that the program counter is pointing to address location 1, which corresponds to location 1 in memory, and we see that the value there is 4. So the computer will take the number 4 from memory and pull it into the CPU. This value is then put into the instruction register. So we know that the location was 1. We took the value that was at location 1 and put it into the instruction register. The old instruction code that was there, 0, is basically deleted. We override it with the value of 4. The program counter, since we have just captured or executed this bit of code in position 1, is incremented to address location 2. And we know that this value is going to be what's placed into the instruction register next. So I hope that makes sense. We started with 0. That was our completed code. We knew that we needed to go to position 1 in memory, which corresponded to this right here. The value at position 1 is the command 4. 4 is then placed into the instruction register for processing. The counter is then incremented to the next command that we will process once the number 4 is executed. So the CPU in the instruction register has the instruction code of 4 and will execute whatever that happens to correspond to for that CPU. When that is done, then the CPU will go ahead and process the next command, which was in position address position 2, and continue these forever. This is how a computer works, and it doesn't matter what you're doing, it will continually update the instruction register and the program counter based off of what you're doing. And we'll talk about how you can branch off to do different things a little bit later. So a pointer is pointing to a location in memory. It's not the data at that memory location, but it's pointing to that data. In computer science, pointer always points to a location in memory. So we saw that the program counter was pointing or held the value of 1, which meant that it was pointing to the location 1 in memory. If it's pointing to location 4, then we know that it's pointing to here. So this is the location address. This is the value at that address. To take it back into programming, if you're familiar with programming, you can have a key and a value associated with that key. Could be a dictionary in Python, could be a hash table, whatever structure you're talking about. And you have a key and you have a value associated with that key. In this case, our key happens to be a memory address, and then we have a data value associated with that address. In C and C++ and several other languages, you have a variable that has a value associated with it, so that variable equals the value. You also have a pointer of that variable, which is basically saying, I don't have a value directly associated with me, but I am pointing to the location of the variable, of the value. We're kind of going off into a tangent. I hope I haven't lost you yet, but just recognize that when you're pointing to something, you're pointing to an address location and not the actual data, because the data can move. I could take this 56 and move it up to memory location 2 if I chose to. And so whatever's pointing at memory location 4 won't see that 56 anymore. It'll see whatever value is then put into there. So the pointer in the CPU is the value of the location. So it's the address location. So if you want to put it into a physical metaphor, the address is the address of your house, and the data is what is located inside of your house. So if you tell your friend, go to this address location, you give them your house number, and get the box that's next to the front door, then they go to that address and they get the data, which is the box, from your house based off of knowing what the address is. Reiterating again, just so you understand what we're talking about when we're talking about pointing to memory. Pointer to the memory location 1 is pointing to this location. It doesn't matter what the data is that's within memory. It just cares about that particular location. So storing the value 1 in a register will remember the location 1, not the data that's in it. The value 1 in the register is pointing to the memory location 1. Same thing for memory location 4. It's pointing to this location and will use whatever data is there, but it doesn't care what that data is. The only thing it cares about is what the address is. Tying this back to what we talked about earlier, the program counter is effectively a pointer to a memory location. So when we have the number 1 within the program counter, it's actually pointing to this location in memory. It's mapped to that. And so that is how the instruction register knows to take the value 4 from that location that the program counter is pointing to and put it into its register. And then the program counter will increment to the next location, and then the next location, and so on and so forth. So we've covered how the functionality of the computer works. Now we're actually going to look at a program flow and see how that interacts with the CPU itself. So program flow is the sequence of instructions executed by the CPU. So if you have your program that you have written it in source code that's converted into machine code that the computer understands, and then that's further broken down into data associated to a memory location when it has been uploaded into the computer for running. So normal program flow is top to bottom. It runs starting at position 0, goes to position 1, goes to position 2, goes to position 3, so on and so forth. And each one of those positions is the next address location in memory for this particular program. Obviously, each program is going to have its own set of memory locations, and so that's how you don't overwrite data. Non-branching basically means that it's sequential. We'll talk about branching instructions shortly. So, as I said, starts at the top, goes sequentially down to the bottom. In this case, we have an add, we have a compare, we have a subtract, a logical AND, so on and so forth. And that's what each one of these numbers within this memory location correspond to in terms of the instruction that is provided to the CPU. If you have a branching instruction, then that means that you can change from a sequential address to a given area, given location that you want. So the CPU executes the branch X instruction, then instead of being sequential, the program counter will point to the arbitrarily determined location within memory. So in this case, we start at 0, we go to 1, and this tells the computer branch to location 4. So instead of what we have seen normally, 0, 1, 2, 3, 4, we skip number 2 and number 3 addresses. We jump to address location 4 and process this command here. So instead of the last time where we had add, compare, subtract, and this time we're going to add, go to location 4, and negate. So effectively what we would see is add, negate, because that's what the computer would do in terms of processing our data. And then it would continue on with position 5 and so forth. But if position 5 had a number 64 in here, or whatever it would tell it to, then it could jump from position 5 down to, say, position 10 and process the command that's there. So before we go much further, I just want to point out that our default processing is sequential, top to bottom, one command, then the next command, then the next command. But you, as a programmer, and by virtue of the conversion to machine code, it doesn't always have to be sequential that way. You can branch out. And so this kind of comes into, if you're a programmer, how you think about your code. You can branch off doing different things within your code based off of specific conditions. You could be using if-else commands. You could be using a switch command, whatever the case may be. But your normal top-to-bottom logical flow doesn't have to be that way. You can have some sort of a condition that says, if this condition exists, go over to this other branch of code and process it, and then come back. And that's basically what we're doing within the memory locations of our CPU. So we basically have the hardware version of conditional branching. So next we're going to talk about the types of instructions that a computer can execute. So the computer has three primary capabilities. It can do arithmetic and logic operations, which we've already talked about. So those are going to be your math functions, and then some sort of logical and or not capabilities. And we're not going to talk about logic operations here. So the results of those ALU operations are typically stored in a general purpose register for use with the commands that the computer is getting. You can do memory transfer operations, which means transfer the contents, the value, at a specific memory location to a particular register in the CPU. Say we wanted to take the value of address location 1 and put it into general purpose register 2. That could be a memory operation that we can do, is we can take it from memory and put it into general purpose register 2. Or alternatively, we can take the data that's in register 1 and put it into address location 3. So you have the option of going from memory to a CPU register, or from a CPU register into memory. And that's how you create data and you process it within the CPU and you store it in memory. And then your next operation, you take that data from memory, take it back to the CPU for further processing, so on and so forth. Finally, you can have branch operations, which allows you to move out of that sequential address location and jump to a specific address location to get that data. So after you have jumped to that specific location, the CPU will execute the instruction there and then continue on in sequential fashion until you get another jump command. So there are two types of branching operations or jumps. One is an unconditional that always causes the CPU to jump to the target location. So it's basically a go to this line and I don't care what's going on. A conditional branch will only cause a jump to that target location, to that address, when a specific condition is met. And that kind of goes into your if-else or switch command. You know, if this condition exists, execute this function, otherwise continue working. And a unconditional branch would be execute this function call. I don't care what the state of the computer is at this point. Basically, this allows you to tell the computer how you want it to function. And this, I don't don't misunderstand me when I'm saying that you as a programmer are telling the computer to do this. It's actually determined by the conversion of the source code to the machine code that the CPU is going to be working with. Whether those branches are going to be conditional or unconditional, or if it's even going to branch, or if it's just going to stay sequential. That really has nothing to do with the programmer unless you are actually programming in assembly language and you are purposely telling it, I want this data value placed in this memory location, and then I want you to go to this address that I specifically tell you. If you do anything that's a little bit higher than assembly language, then the compiler or interpreter is going to handle that for you. But all that aside, those are the three types of instructions that a CPU can handle: branch instructions, memory transfer, and then arithmetic and logic operations. So that's it for this video. We talked about the instruction operation of the CPU, we talked about program flow, and we talked about the types of instructions that a computer can execute. So, kind of bringing this over into programming and cybersecurity, a lot of what happens within a computer can be traditionally known to someone who spends a lot of time at the low level functionality of a computer. What I mean by that is, if somebody is trying to hack into a system and arbitrarily execute code that they want to do rather than what would normally be done, they can write a program that will go through, your normal sequential actions and then arbitrarily jump to some position in memory that is normally not even known for use in terms of that program. And then they implement what's called a no-op sled. So that is a no operation, and a no operation means there's nothing for the CPU to execute, go to the next memory location. And so they'll go to an arbitrary memory location, create a no-op sled of, say, 30 no operations, and then it will get to a location within memory, and then that hacker will start uploading their own commands, and because the computer's effectively dumb, it's going to go to that location and start processing those commands sequentially from there. Obviously, there's more details to it than I'm providing here, but I'm just kind of trying to tie how a computer works with cybersecurity, with programming. It's much more in detail than I can provide here, but just recognize that all of the videos that we are creating on this YouTube channel tie in together. It just may not be obvious at first glance how that all ties in together. Getting back on track, so we talked about how CPUs work. We took a look at the different parts of a CPU diagram with multiple cores and the I/O ports and things like that, and then we looked at the block diagrams of how the registers are used in conjunction with your RAM to actually process and execute the commands that are given to the CPU. We haven't covered everything on motherboard, but at this point, I mean, that's about the only thing that's really left to just talk about the video card and what's there to say. It takes the data and it puts stuff on the screen. So there's not much to say about that. But I do kind of want to move over into basic electronics theory, talk about voltages and currents, how those tie into making a computer work, and then get into very, very basic transistor theory so that you can understand how your digital circuits are actually created by transistors to do what they need to do. So this will be probably several videos for the basic electronics theory, because I expect it's going to probably take several hours to cover all of the basic fundamentals of that. I hope you found this video entertaining, or at least interesting. If you have any comments, please let us know. Shout out to Dr. Chung again for allowing me to use his slides. If you have any suggestions for further content, please let us know at the channel. Until next time, keep learning, have fun, and don't let the pandemic get you down. Bye.